Okay, so in this video we're going to look at applying our logic gates to ladder logic diagrams. So we're going to compare the logic functions and how that's integrated into ladder diagrams so that we can better understand these control circuits and how the switches behave in order to control the output. So it's important to understand the logic functions with these switches so that when you have to troubleshoot these control circuits, it makes it easier when you understand how the logic is applied with the switches so that you can more quickly and efficiently troubleshoot ladder logic diagram control circuits. Okay, so before we get into looking at the diagrams, we're going to look at a little bit of information, a little bit of background before we jump into that. If you don't have an extensive background in motor control circuits, this kind of gives you a little bit of introduction into that before we look at the actual diagrams. Alright, so the first thing is we are looking at the two categories of the switches. Okay, so we have what we call normally open switches and normally closed switches. So this means their normal state. So they're non-activated or non-energized state when we're talking about control components. So normally open means that the switch is open when it's not being activated. And normally closed means that the switch is in a closed condition when it is not being activated. Okay, so that's kind of the two categories that we have. Either normally open switches or normally closed switches, and those are always abbreviated NO and NC. Now there's many different types of switches to control our process. Okay, so they can be anything from simple manually operated push buttons and selector switches to more mechanically operated switches like limit switches, temperature, flow, pressure, and then we even have sensors that can do even more advanced control over the processes. So there's many different types of switches just for different applications, but they're all either going to be in a normally open or normally closed state. Alright, so when we look at integrating this with our ladder logic and with our digital logic, one thing we have to understand is whether we activate the switch or not activate the switch when we're looking at the logic and also writing out the Boolean equation for it. So if we just write the input, whatever that input is, then that means the button or switch must be activated or change state for the output to be high. So for example, PB3, so that's just a push button. That means we have to push that button in order for the output to come on. So that means it's normally open. If we have the input inverted, remember we represent an invert with our line over the top, that means that the button or switch must not be activated in order for the output to be high. So in this example I have LS7 not. So that means it's a normally closed limit switch. Okay? So here we have the basic rules for applying our logic to switches. Alright, so we're going to look at actual examples of these in a minute, but I just want to kind of go through these to give you an idea of what we're going to be looking at. Alright, so here I've listed on the left each of the logic functions and then a description of what you'll be looking for. Alright, so for not logic or the inverter, that's just one normally closed switch. Okay, so remember our inverter only has one input. So all the other ones have two or more, but the inverter is only one switch. So if I have one normally closed switch controlling an output, then that means we are doing not logic. All right, so for the AND gate, that's going to be 2 or more normally open switches in series. So remember, all of our other functions have to have 2 inputs at least. So if I have 2 normally open switches in series, that is AND logic. OR is really just the opposite of this. So we have 2 normally open switches that are in parallel. Okay, so I can activate one or the other to make the output turn on. So that is OR logic. 2 normally open switches in parallel. Alright, so NAND and NOR is a little bit confusing because of the operation. So remember, the NAND and NOR is just an inverted output of the AND and OR function. But to do that, you have to change the switch type as well as the connection. Alright, so for the AND, for example, it has 2 normally open switches in series. So you immediately want to think, well, if I just do 2 normally closed switches in series, that would do the same thing for a NAND. But it does not. So for a NAND, you have to have 2 normally closed switches in parallel. Okay, so it's the opposite type of switch and the opposite connection. So the same goes for the NOR, and that should be normally closed, by the way. So 2 normally closed switches in series, opposite connection of a parallel. So NAND and NOR have to be the opposite types of switches and the opposite connection. Okay, so just remember that. So it's not only the opposite type of switch, but the opposite type of connection. Alright, and then we have the exclusive gates, and remember, that's our kind of specialty operations for comparison. So you're not likely to run into this an awful lot with ladder logic control, but it can be done. So for the exclusive OR, you have 2 mechanically connected, normally open and normally closed switches in series. And for the exclusive NOR, 2 mechanically connected, normally open, normally closed switches in parallel. And that probably makes no sense at the moment, but when you see the application, it will. Okay, but that is your connections that you're looking for. So again, the type of switch that you use is not really important. Doesn't matter if it's temperature, pressure, flow, push button, limit switch, whatever. These connection types is what gives you the different types of logic. Okay, so let's jump in to the diagrams. Alright, and I'll put the list over here where you can see that. Alright, so the first one here, I've got 2 limit switches controlling a solenoid. Alright, and both of these limit switches are open. Alright, so I have 2 open switches in series, so that means that we're talking about AND logic. Okay, so to write the expression here, I have LS1 and LS2 in series. So if it's AND, remember that that is multiplication. So the solenoid equals LS1 times LS2. Okay, and that would be my Boolean expression. So it's doing the same thing that we did when we first talked about the logic gates. Here we're now actually using the inputs and outputs as part of our control system. So instead of calling it A, B, and output Y, we're actually putting in the switch names. All right, so we can build a truth table for this as well. So LS1, LS2, and our solenoid output. All right, so remember how we set this up. So it's 0, 0, 0, 1, 1, 0, and 1, 1. It's in order numerically. So if I don't close either switch, there's no path for current flow, so the output is off. If I only close LS2, this one's still open, so the solenoid's going to be off. If I only close LS1, there's still no complete path for current flow, so the output is off. If I close both limit switch 1 and limit switch 2, then I have a complete circuit and the solenoid will be on. Okay? And just to back up here for a second, in case you're not familiar with the motor control ladder logic, so these rails are your power. So this can be positive and negative if it's DC, or this can be hot and neutral if it's AC. So closing the switches, we have to have a complete path of current flow in order to energize that output. Okay, so that's how that works. So that is AND logic. If you have open switches in series with each other, that is AND logic. Any low gives you a low. That's our rule for it. So if any switch is open, that output is going to be off. Alright, so next we have the limit switches in parallel with each other, controlling the solenoid, and they're both normally open. So that is our OR logic. When we have two or more switches that are normally open in parallel, that is OR logic. Alright, so for the expression, remember for OR it is addition. So LS1 plus LS2. Alright, so we can set up our truth table for this as well. LS1, LS2, and our output solenoid. So remember, we do this numerically. 0, 1, 2, 3 for counting in binary. Alright, so if neither switch is activated, no path for current flow, solenoid is off. If I only close limit switch 2, now I have a complete path for current flow. Through that one switch gives me a complete path, so the output is high. If I only close limit switch 1, that gives me a complete path for current flow to the solenoid, so the output is high. If both limit switches are closed, there's a path for current flow, so the output is high. Okay, so that gives you the output results for an OR gate. Remember our rule, which is any high gives you a high. So any switch that's activated will turn on the output. Okay. Alright, next we have a single limit switch controlling the solenoid, and it is closed, so that is not logic. Okay, so we only have a single input and it's closed, so that's not logic. Alright, so to write our expression, the solenoid equals LS1 with a line over it. LS1 not. So that means I do not activate that switch and it's going to be on already because this is closed. So if power is established on this control circuit, the solenoid is going to come on immediately without activating the switch. If I activate that switch, it's going to open and then the solenoid turns off. So if I write my truth table for this, it's just one input, one output. So only two possibilities, 0 and 1. So 0 means I don't activate it. Okay, so don't confuse that about being open and closed and activated and not activated. Alright, so 0 means I don't activate the switch. So if I don't touch that switch, it's already closed, the output is high. If I activate that switch and open it, then the solenoid will turn off. Okay, so when you're looking at the ones and zeros, remember that's going to represent, do we activate the switch or not activate the switch when we're looking at terms of logic, not whether it's physically open or closed. Alright, so our next one's here. So now I have, in this one, two normally closed switches in parallel. Okay, So remember I said when we're dealing with closed switches and opposite connections, that's what we get for our inverted output. So remember the AND was two opens in series. So here we have two closed in parallel. So that is our NAND logic. All right. Now with the expression, I'm going to write this out two different ways. All right. So the actual representation of what we have here is two closed in parallel. So actually this is LS1 not plus LS2 not, because they're in parallel. So that is an OR function because they're in parallel, but they're normally closed switches. So I put two lines over it. All right. So that's actually what's going on. But the equivalent output operation gives us LS1 times LS2 not the whole thing, which is the NAND function. Okay. So that's actually what we have. That's what the output result will be. Okay, this is just a different way of looking at it. Okay, so this is actually what it is, but this is the output equivalent. So if we look at our truth table, LS1, LS2, solenoid output, write our input conditions. Alright, so if I don't activate any switch, they're both closed, so that solenoid is going to be on. If I activate only LS2, so that's just going to open that, 1 is still going to be closed, so the solenoid will still be on. If I only activate 1, 2 is still going to be closed, so the output is on. If I activate both 1 and 2, that opens both switches, so that turns the output off. Okay, which is exactly opposite of the AND, so that is the NAND operation in a ladder logic diagram. Okay. All right, so the next one is our NOR function. So again, if we look at the OR gate, is two open switches in parallel. If we go to the opposite type switch and opposite type connection, that makes it a NOR function. So we're going to have the same kind of deal with our expression. So actually what this is LS1 not times LS2 not, because they're in series with each other and they're normally closed. Of course, the equivalent of this is LS1 plus LS2, not the whole thing, which is the NOR gate. Okay, so if I look at my truth table, LS1, LS2, and my solenoid output, running out of room there. Alright, so if I don't activate any switch, I have a complete path for current flow and the solenoid is on. If I open or activate LS2, that's going to open it and I no longer have a complete path, output is off. If I only activate 1, that's the same thing, no path for current flow. If I open both, no path for current flow, output is off, so that gives me the equivalent NOR logic. Alright, so the next two are my exclusive gates. So the first one is the exclusive OR. Alright, so what I have here is two push buttons that have two sets of contacts on them. So this technically is still just two inputs. But it's actually 4 connections because each switch has 2 sets of contacts. Alright, so this dashed line here means that they are mechanically connected to each other. So when I push this button here, A, it's going to close this one, but at the same time down here at the bottom it's going to open this one. So the same thing happens when I push B. If I push B and open this top one, it's going to close this bottom one. Alright, so that's what we have to do in order to get the exclusive function. Alright, so if we write this out in terms of the Boolean expression, so we're controlling a pilot light this time instead of a solenoid. So the pilot light equals, so let's look at each contact. So we have a normally open A, and then it's in series with a normally closed B. So that's A times B naught, plus, because we have a parallel connection, then we have A closed, so that'll be A naught in series with B again that's normally open. Okay, so that's the actual expression of what's going on. A times B naught plus A naught times B. Of course, we can simplify that by just writing the exclusive OR expression, which would be A exclusively OR B. Alright, so if we put in our truth table here, okay, so we got push button A and push button B. Alright, so if I don't push anything, if I don't push either button, there's no complete path for current flow because this is open here, this is open down here, so there's nowhere for current to get to energize that light, so the pilot light is off. If I just push switch B, if I push that switch, this is going to open, but down here, this one's going to close. So this is normally closed and this will close, so that provides a path through this bottom line to energize the pilot light. If I let go of B and activate only A, this will close, B will remain closed, and the pilot light will be on through the top line. If I push both A and B, A closes up here but opens down here, and B opens up here and closes down here, so it becomes exactly the opposite, so there's no path for current flow. Because this will be closed but that'll be open, so it can't go that way. This will be closed but this one will be open, so it can't flow that way. So that gives us our exclusive OR operation, where like inputs give you a low, unlikes give you a high. Okay, so a little bit strange and unusual for the exclusive gates, but remember that's only kind of special applications where we use that. Alright, so down here's the exclusive NOR. So it's basically the same kind of setup except a different arrangement of the open and closed. So on the exclusive OR we had open, closed, closed, open. Here we have open, open, closed, closed to get the exclusive NOR operation. So if we write the expression, we have AB plus A naught, B naught. Okay, so they're open up here, so A and B, or A naught, B naught. Of course, we can write the equivalent here, which is A exclusively OR B naught. So if we look at our table again, if I don't push anything, the pilot light is on. Why? Because down here on this bottom line, these are both closed, so the pilot light is going to be on. If I just push B, that's going to open this down here and close this up here. So now there's not a complete path through the top or the bottom line, so the pilot light is off. Okay? If I let go of that and only push A, then B is open, A is closed, so no path for current flow, and A is open down here, B is closed, so no path for current flow, so the output remains off. Then if I push both A and B, both of these at the bottom will open, but both of these at the top will close, so my pilot light comes on again. So there gives you the like inputs give you a high, and the unlike inputs give you a low. All right, so you can apply this to any ladder logic diagram, just looking for these different connections. So this is all the logic functions and the examples of how those switches are connected to get those different examples. Okay, so these are individual that I pulled apart. Of course, a ladder logic diagram is a big long diagram with multiple lines in it, but you can pick apart these connections to better understand how the outputs are supposed to behave and therefore be able to troubleshoot them more efficiently. Okay, so I hope this gives you a better understanding of applying our digital logic gates to ladder logic diagrams. And if you have any more questions about this, you can let me know. Thank you.